On this week's MetPy Monday, we're going to learn how to fit polynomials to data so that you can get lines of best fit on your data in just a couple lines of Python. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. On this week's MetPy Monday, I want to show you how to do a relatively simple task of fitting polynomials to data. It's a common issue when you're doing calibrations or cross-plotting where you want to fit, say, a line or a quadratic or a cubic function or even a higher order polynomial to your data. And it's really just a couple lines of NumPy to do this, and I don't think that a lot of folks are aware that you can do this and still are opening up Excel or hand coding an inversion routine that you don't really need to do. So first we're going to do our imports. We're going to be using NumPy. So import NumPy as MP. And we're going to be using matplotlib. So import matplotlib.pyplot as PLT. And we're going to use our inline magic so that our plots show up inline in the notebook. Next, we need some data that we're going to fit. So I have constructed some fake data before I started recording this video using an equation that I know. So we'll see how close we get to that equation at the end. So this comes from y equals 3.45 times x plus 2.12 plus noise. So my x values that I'm going to fit are 0, 2, 3, 5, 6, 7, and 9. The y values that correspond with those are 1.66, 8.29, 13.64, 18.45, 21.51, 26.77, and 32.93. And I'm going to go ahead and make these NumPy arrays. So we wrap that list in np.array. So now let's make a plot. Let's just look at the data, see what it looks like. If we didn't know what the equation was that this came from, we might not know what order polynomial we should be fitting it with. So a figure and an axis. I'm going to create those by calling plot.subplots, which returns both of those objects at once. And then I'm going to make a scatter plot of x and y. And I'm going to provide the label of raw data. So let's see what that looks like. So we can see this does look pretty much like a line. There's a little bit of deviation from the random noise that I added to the data. So now we need to fit that. So I'm going to go ahead and insert a cell above. We determine the coefficients for a polynomial to fit data using NumPy's function Polyfit. So I'm going to say the coefs equal np.polyfit. And if we look at the docstring by pressing Shift-Tab here in the notebook, we see it takes x, y, and the degree of the polynomial that we're going to fit. There are some other optional arguments, but the defaults on those are fine. So we have three required positional arguments, x, y, and the degree of polynomial. So a degree 1 polynomial would be a line, and that's what we're going to use. So let's do that. And print coefs. And I'm going to insert a couple of cells here. So what we get with coefs are the coefficients from the highest order to the lowest. So this would go with x, and this is the intercept. If we had a quadratic, we would have the x squared, x, and then the intercept, so a, b, and c. So go from the highest order to the lowest. So you remember my original equation here, my first coefficient was 3.45, so we nailed that pretty much dead on. The intercept is a little off, but not too bad. So now we want to plot our fit on the same graph that we already have. So to do that, we need x and y fit values. Now we could use the original array for x, and that works fine for lines, but when you go to higher order polynomials, you're going to get straight line segments between each of those points that you're plotting, so you generally want to use more x values than your data. So I'm going to make x fit. This is just the generic way that I like to do it. And I'm going to make that MPA range from 0 to 9, because that is going to match our data range. Then y fit. Now you might be tempted to start typing out the equation based on these coefficients, but we can do even better than that. You say, well, yeah, I could pull out the coefficients by index and use that, but we can do even better than that. And that's by using NumPy's polyval function. Now, why would you use this instead of coding it yourself? Mostly because this can take any arbitrary number of coefficients, construct that polynomial, and return the results to you. So we can very easily change our order of fit and see the results. And we'll do that in just a second. So if we look at its docstring, again, Shift Tab, it takes the coefficients and then the x values. So I'll give it my coefficients and my x fit. I'll remove a couple of the extra cells now. If we go to our plot and plot x fit, y fit, label equals best fit, there we see a line of best fit. Now I can go up here and change the order to, say, a second order polynomial. Rerun those cells. And really it doesn't look that much different because that first term is very small. Now we have 1, 2, 3, 4, 5, 6, 7 values in here. And we know that you can perfectly fit in values with a degree n-1 polynomial. So if I make this a sixth order polynomial, it should hit every one of my points perfectly. But that's obviously overfitting and not what we really want to do. So I'm going to go back to a first order polynomial. And now we're going to turn our attention to the plot a little bit. We can go ahead and give some labels to this. So set x label of x data. I'm going to give it a font size of 16, so it's a little larger. Set y label of y data, font size of 16. Okay, that looks better. And then finally, I'm going to call ax.legend, because now those labels that we typed in give us a nice handy legend for the plot. Granted, here it's relatively simple, but let's say we had multiple lines of best fit. Well, we can do a little better yet, and that's by displaying the equation of best fit instead of saying best fit. So to do that, we're going to change this label. I want to make it something called an f-string, which we've discussed before on MetPy Mondays. And then we'll type the equation. So y equals, and then in brackets, remember, is what we're going to replace with a variable. So coefs 0 is the highest order. Coefficient x plus bracket coefs 1. Now we have the best fit equation displayed there. Now granted, if we change to a higher order polynomial, this is only going to show 2 of those coefficients, and they're not going to be the right ones. So you would have to generalize this a little bit more, which you could certainly do. But for now, let's go ahead and finish dressing this up. I don't want all of those digits after the decimal, so I'm going to put a colon and 0.2f. And the same here, a colon, 0.2f. Now when I run it, I get nicely truncated floating points. So y equals 3.45x plus 1.83, which is pretty close to our equation that I started with of y equals 3.45x plus 2.12. So I hope that you found this useful, and if we get a lot of feedback on this, we can go more in depth into doing some basic inversions or writing functions to generalize things like this string formatting. So go ahead and leave a comment down below, and I'll see you on next week's MetPy Monday.